Okay, let's get started. Howdy. So today is our last lecture. And in fact, the last possible class for 766 is next Thursday. Because the Tuesday after that is going to be a redefined Friday. Then it's end of the semester. So the arrangement is the following. Today is our last lecture. Next Tuesday, we don't have any lecture, and you just take that time for your final project. And you can also use that time to meet with me, right? So for the help. So then on Thursday, we have the final project presentation. Everybody knows, right? That's not the news. Next Thursday. So each has 15 to 18 minutes, because we have 4 or 5 talks. Some of them have been sick, you probably have noticed, for missing too much of the semester. So they won't be available. But we should have at least 4 talks, or maybe even 5 talks, each 15 minutes, including question and answer. So that's what it's about. And you know what the presentations usually consist of, right? Very much like your proposal plus midterm update plus some outlook and conclusion. It's possible that when you do the final presentation, your results are not complete yet. It's still worthwhile talking about what you have now and what else is being expected and what are the barriers ahead. So there still should be 1 or 2 weeks, 1 week maybe, for the final paper submission, right? For some of you who are not degree candidates, maybe that can be even extended a little bit, right? I think the current deadline is to make sure that at least degree candidates can get their everything graded, okay? I think I have your first 2 homeworks graded. I'm still missing some grade homework 3, but I guess I just have to grade homework 3 and return back to you. I will add the journal club presentation scores onto Canvas, and also give you back the proposal and midterm. The reason I didn't grade them earlier was I thought I already talked with you about the proposals and the midterm report after you submit them. So I thought the feedback part was already there, but I will give the scores back. But the proposals and the midterm reports all look good, so not too much to worry about. So we are at the last lecture of the class, and just want to remind you where we have come along so far. So more than 50%, I think, 6 or 7 weeks have been focused on deep learning. We actually started, right? But just remind us where we have been, right? We used the first few lectures talking about the problem, right? And why it's a very exciting frontier, especially now that AI is coming into the play, right? We talked about the classical formulation and methodology for the protein structure prediction problem, as well as protein function prediction problem. And we used these 2 motivating examples to showcase optimization and machine learning. I know you have learned about the basic concepts about optimization, linear, dynamic, integer programming, and the numerical optimization methods. You see numerical optimization methods later on came up before we talked about the recurrent neural networks, because we talked about the computing that's needed for deep learning, including the backpropagation, right? Stochastic gradient descent. What is the stochastic gradient descent? What is the batched stochastic gradient descent? What is the vast stochastic gradient descent with momentum, right? AKA atom. And then we really, as I said, in the past 6 or 7 weeks, we have been focusing on the data perspectives of these problems. You have different formulations, partly because the data are becoming increasingly available. You have 180K structures, right? And computing is getting easier, and there are a lot of things has been happening now in AI. So a lot of reasons, right? Remember you learned first about the image data. Sorry, actually before that, I think we first talked about the grid data and the MLP, right? Deep learning and the MLP, right? We talked about those tabular data first, right? Then we asked about what about just doing the computer vision task using MLP and treat the gridded image data as if they are just the tabular data. What was the problem, right? That was the first problem that we encountered, that we have to design an architecture to smartly address the challenges that we are facing, right? We got the inspirations from how human visions work, and we translated those visions, those insights, into mathematical operators like convolutions, right? With shared and sparse parameters, right? With pooling, right? With all kinds of operations. Then we, talked about the neural network computing afterwards, right? Because all of this are driven by the technology that can help you train the machine learning models effectively, not bothered by the depth issue, right? As we see later on, especially in the recurrent neural networks, when the recurrency is a blessing, but it's also a curse for back propagation or training, right? And we learned that how that has been addressed by the modern architectures like LSTM and GRUs. And more importantly, they can be further addressed by completely removing this sequential recurrency, right? Using attentions alone. Attention is all you need in that paper, right? And we talked about how these attentions work and how this modern transformers look like, and how you can pre-train these transformers, like whether you are pre-training the encoders or decoders or encoder-decoders together. The important thing is that you have to make sure that you are utilizing a lot of unsupervised data when pre-training the transformers, yes, but you also have to design your pre-training tasks very carefully so that the majority of your models or model parameters have been already trained and can be used as a warm start in the fine-tuning stage when you have the supervised, right, machine learning tasks. And that is not easy, right? But we have seen so much like BERT or GPT, how their pre-training tasks look like, right? So, what gonna happen today is, we talked about, transfer or, self-supervised learning there. So we also talked about the generative models right afterwards, and then we'll combine them actually today. For instance, when we introduce this new roto-translational equivariant networks to model the 3D point clouds, right? Of course, you can use 3D CNN, but keep in mind that CNN is rotationally variant, right? It's translational invariant. So if you don't want to use the low efficiency approach of data augmentation by randomly rotating every sample multiple times, right, then you may want to consider a more powerful method that explicitly having that constraints of roto-translational equivariance in the network architecture, right? So that's something we'll talk about in today's journal clubs, right? And then we can see how these different architectures can be combined or utilized in different purposes. For instance, in your generative networks, right? So the plan is the following for today. The last lecture will finish up transformers, okay, with two latest developments. Basically, we'll finish up the generative models by incorporating the transformers or attentions. So that's two latest development about the generative models, right? That's where wrap up first. Transformers are really becoming a universal architecture now for different tasks, so definitely paying a lot of attention. Secondly, we will go over a few papers very quickly at a high level to show you again additional protein design or drug design progress. Okay, I will talk about 4 papers, but the last paper I will skip or skim because that's exactly what Ryan is going to talk about as well. So in that second part, I'm going to focus on 3 of the 4 protein design or drug design paper. And lastly, we'll have 2 talks about the equivariant neural networks, and one is a discriminative model and one is a generative model, okay? And in the end, we should have about 10 minutes-ish so that we can do the course evaluation. We have a small class, and 1/3 of the class has been sick for a while, so it's very important to have your feedback on how to improve this course, right? And your opinion matters a lot for the future participants, okay? And thank you very much. Well, now let's start talking about what has been going on in the recent generative adversarial networks, right? So we talked about this very briefly as well, that things has been going on several directions, right? So there's this GAN zoo and a lot of development. This probably finished a few years earlier, right? But there's more since then. And the new developments included the loss functions, right? Like Wasserstein GAN instead of using the Wasserstein distance instead of the Jensen-Shannon divergence we talked about last time for training GAN, right? There's also conditional GANs, right, where you put these desired properties as an input condition for this conditional GAN, right? But a lot of things you have to think about in this way, that you basically see other papers do things like that, okay? And then they don't really talk about a lot about why they do things like that. A lot of them were because of convenience, or I can calculate it that way. And they try to argue that the results are not too bad. But if you really think deeper, there's not a good reason to do things like that. Like, why is it a good idea of treating this desired property as a condition, and then this condition and the random noise are both used as inputs to the GAN and in some specific way, right? That does not necessarily make perfect sense. So I think in this area of information explosion, right, sometimes we don't even know which is information, which is disinformation, when every paper is saying that, look, we do well, right? You don't see a paper say that, well, look, we tried this, results really bad, right? You really need to figure out what is real and not be biased by the majority, actually. The majority or the mass might be the followers, and they contribute to a trend that already is there. They make things hotter. But that doesn't mean that you can take the majority vote and just believe what they say. So this is a tricky thing. So the recent developments, I said, beyond these, better loss function and the conditional GAN, right? What else can you do for GAN? One thing, apparently, after we learned using 3 lectures to learn transformers, you probably figured out, yeah, this discriminator generator in GANs don't have to be CNN, right? Don't have to be MLP. What about self-attention layers, blocks, or transformers? Well, the thing is the following. Yes, it's a great idea. It's a great question, right? But remember, if you work in these kind of topics, it means like there are a lot of people who are just like as smart as you are and as hardworking as you are, they are also asking a similar question, right? Then it's just about, who can do it faster and smarter and deeper, right? So I think we need to resist the temptation of, just trying to beat everyone to be the first. That adds a lot of anxiety. Of course, you need to deliver things in time, but you cannot just live to become the first all the time. Sometimes you need to be the best or someone who really understands things. So I want to show you that there are two papers, both published, right? Addressing the general question I was asking, right? I'm going to ask you, what do you think? Which paper got more citations? But again, citation is not an indicator of success. But just for fun, I may ask you which. But more importantly, I want to show you that, look, you could have very diverse research and you can contribute to this whole knowledge in your own perspective. So cherish your own unique perspectives, okay? All right, so the first paper is called the TransGAN, okay? So the title is called Two Pure Transformers Can Make One Strong GAN and That Can Scale Up. So, the title says everything, right, pretty much. And you can click for the paper and a talk, okay? I'm gonna just, I'm gonna talk about the high-level things. So I took some sentences from their abstracts, and I want you to pay attention to these points they made, okay? So they had to do this was something they were aiming, and not necessarily that was the first, but the aim was to have a pilot study, right? In building a GAN completely free of convolutions, right? So apparently they are also looking at computer vision tasks, but completely free of convolutions, because the background is that 2019, 2020, right? People see that transformers are, not only flourishing in natural language processing, they are also, making solid impacts in computer vision. Then people start to think whether transformers can be the universal architecture, right, for different kind of tasks, right? So, and then that's what their goal is, right? So that doesn't mean that it's easy to answer a question, right? Just think about again. After I said, well, let's just treat it as two-player game. You can train your generator by co-training a discriminator, right, in this way. But there's still a lot of things. Remember, in the computer vision, right, you had to use different architectures of CNNs, right? You have to use, you have to do this upsampling, right, in this generator, and that probably involves some changes. But here, this vanilla GAN architecture consists of a generator and a discriminator, okay? But the generator, of course, is transformer-based, but the issue is that, as we said, biggest con of transformer is memory, right? So apparently they, face a challenge and address that challenge, which comes from the memory. So this keyword is memory-friendly generator, okay? And in the case of the discriminator, is multi-scale that can simultaneously capture semantic context and low-level textures. So that's their contribution, okay? And on top of the two architectures for the generator and the discriminator, they also have to, do something for the self-attention, right? So they have to introduce this new module of grid self-attention, again for alleviating the memory bottleneck further, okay, so that the TransGAN can scale up to high resolution generation, because this is for high resolution image generation. It really needs to scale up, but the memory issue that transformers face in both, in this generator case and the corresponding self-attention in the generator, both need to be addressed. And lastly, besides the model architecture, there's also, objective function and how you train this model under the objective function or loss, right? This training recipe includes a series of technologies that can mitigate the training instability issues. As we know that training GANs are difficult, right? So there's this instability issue. You could really lead into mode collapse issue, right? Where the generator just keep generating one kind of thing because that thing is enough to fool the discriminator, right? And then for this issue, they have to utilize a series of techniques like data augmentation, modified normalization, and the relative position encoding. So this is related to the position encoding, right? If you think about it, again, we have a lot of things we don't understand about the positional encoding, right? Do you concatenate or add them? What is the base of adding them? And then what is the base of designing this positional encoding? It's really funny that in the transformers, the self-attention don't care or have an idea about the order, but then you have to artificially put that order information in to the input features and let this combined thing, whether concatenated or added, feed through the same self-attention layer. I mean, I know it's done in that way. It doesn't mean that it makes, it doesn't mean that that has to be the way. So the less we assume things have to be done in that way, the better. The less we know, we say that we don't understand, the better actually. So this is the first paper, okay? And let's take a look at these, a little bit about the generator discriminator, and this is the architecture, right? So this is the generator, right, which basically goes up, right? So this that has to start from the noise and generate a very high resolution image, RGB 3-channel, 256 by 256. And it needs upscaling and the transformer blocks, and then this is the discriminator architecture, okay? So the second paper is Transcan, okay? I'm sorry, this is still Transcan, but there's one, this is still the first paper, but they compare Transcan with the GAN using convolutions. So you may wonder, how can you explain what is happening, right? They were sort of showing these training dynamics. So as the training epochs increase, they see what kind of images are generated in between, right? You see that they are looking at different things. Do you see what I mean? Right? Do you see what I mean? The way images gets clearer and clearer are different in these two kind of models due to the difference between convolution and self-attention, right? Right? If it were you, how would you summarize the difference in this pattern in a way to connect to the difference between the models, aka convolutions and self-attentions? That's a practice for you, and you can look into the paper and see what's your answer. This is very similar to the Ramachandran plot I was saying. Well, this is the consequence. The pattern looks like this way. Do you have an explanation to this? Does this match your expectation, or does this surprise you, right? So this is actually closely related to the difference between the self-attention and the convolution, okay? The second paper is VIT GAN. The background is that there is a, as I said, 2019-20, the transformers entering the computer vision, and then one of the success model is called vision transformers, right? It's very competitive in this case, right? So then they are asking, well, can I, again, extend these vision transformers to image generation, right? Then for generation, of course, I'm thinking about GAN, right? So they're asking, well, can I integrate this architecture into GAN, right? So this is very clear, and again they did something similar. They have to do something differently for discriminator and a generator, right? So They noticed that in the case of the discriminator, the existing regularization methods for GANs interact poorly with self-attention, causing the instability. So their ways to get around is to introduce several novel regularization issues to train the GANs. So that's their one contribution. The other one is for the generator. They were just examining how the architectural choices for latent and pixel mapping layers can facilitate the convergence, right? This is the second paper, right? And this is the overview, right? So you have the generator here, right? The latent variable, it maps, and this is some encoder using the self-attention transformer layers, right? And then there is then this for embedding an MLP, right? And then the generated patches are again just row-wise arranged into this very generic vector, and then sent to the discriminator, right? Which goes through not only the embedding, but also there are some position as well. You see this position, right? Positional encoding, and then in the end they make a classification. Okay, any guess which paper got more citations? VIT GAN. Training GANs with vision transformers, which is iClear 2022 Spotlight. TransGAN, 2 pure transformers can make 1 strong GAN and that scale up. NeurIPS 2021. It's not like I'm trying to teach you something, but just curious, based on your taste and your understanding, which one got more citations? It's not like citation is the only indicator of success. It's not even the indicator of success. Not necessarily. Any guess? TransGAN or VIT GAN? Let's see. Who think it's TransGAN? 1, 2, 3. Who think it's VIT GAN? 1. Okay, you can find the answer by Googling. Okay, but again, whether you are right or wrong doesn't say anything about it. As I said, it's more about your research taste and understanding, and also it's very important that no matter what you did, at the end you need to tell that to the community. How you present your results to the community also matters.